QGIS tutorial will demonstrate how to create a raster, specifically in this case a hazard raster, for unstructured scattered data. And in this case, we're going to be using some output that we pulled from the coastal hazard system from the South Atlantic Coastal Study. And we're going to interpolate this to create a regularly spaced hazard raster over Dolphin Island. So I've got QGIS pulled up, and the version of QGIS here I don't think is important because the steps are going to be fairly consistent regardless of the version. But just for grins and giggles, this is version Lima 3.32.1. I've already got Google Satellite pulled up in the back just to give us some visual reference of where our data are going to be. I've already got the data prepared in CSV files for the 50, 100, and 500 year return period events, again, as determined by the South Atlantic Coastal Study. So we're just going to pull those CSV data in. So I'm going to use the data source manager and the delimited text option. I'm going to navigate to the location of that file, which in this case is in this folder, and I'm just going to pull out the 50-year return period event for reference, and just to get going with something. If we were to look at the file, expand this a little bit, you would see that there are 5 columns in there. There's a longitude, latitude, the still water level, the significant wave height, and the peak period. And so that's going to define the data that are in there. And there's headers in there in the file that explain that. So depending on what boxes you have checked in your data source manager for loading delimited text, if you have it look like this, then it should load in pretty easily. So our file actually, the columns are tab separated, but if you have tab or space, usually I just have both of them selected and it works fine. Actually, this is just a text file. It's not even a CSV file. It's just a plain text file that was written out from MATLAB. I've got these boxes checked here. So first record has field names. It's going to try and automatically detect the type of data. So in this case, they're all real numbers. Trim fields. So if you've got empty ones, get rid of them. And reduce the number of columns, and then discard empty fields. So just skip them. It should pull in, if you've got columns labeled like X and Y or longitude, latitude, or lon and lat, it will identify those as X and Y coordinates. And in this case, you can see that we're using a geographic coordinate system. So this is in longitude, latitude, which generally corresponds to World Geodetic Survey 84, WGS 84. So those are the settings that you'd need to mimic on your system to read in these text files that we've created for the Dolphin Island example specifically. So I'm going to click Add and close that, and you'll see all of our points pop up here. I'm going to change the color just a little bit so that they pop out a little bit better. So that's what we're working with. You see that the points are more closely spaced together along Dolphin Island, but there's still not a lot of them. But we've got this big field out here around Dolphin Island from which we can interpolate some data. But Dolphin Island is relatively thin and fairly small relative to what's going on in here, and not a lot of points. So after working with raster creation, you'll be able to kind of immediately look at the data that you have and compare it to the area over which you're trying to interpolate, and you'll immediately have developed some intuition about whether or not this is going to work well or not. And in this case, you can kind of produce something that is, for the most part, good enough, but it's not great, and it's just relative to the spatial scale of the data or the resolution relative to the area over which we're trying to do the interpolation. But it's better than nothing, so enough with the commentary. We'll just move ahead. First thing we need to do is actually, well, the first thing I would do is convert this text file into a shapefile so that QGIS understands what we're trying to do with it. So over here in the layers window, I'm going to right click, select and right click that file. And I'm going to do export, save as, and I'm going to save it as a format type Esri shapefile. And I'm going to save this in the same folder that we're working in right now. So this will be DI 50 year, and I'm just going to put shape in there just to remind me that when it pops up in the layers menu over here that I'm looking at the shape file, not the text file. At this point, you really don't have to change anything else, but to reduce the number of steps here that you need to do, I would recommend going ahead and converting your coordinate reference system right this very minute, because we know we're going to interpolate these data, which means that geographic coordinates will not work. So we need to convert this to a flat or projected coordinate reference system. And in this case, we're specifically going to convert it to UTM zone 16 north, UTM zone 16 in. So I'm going to select my drop-down menu over here in the CRS box. And because I commonly use this coordinate reference system, it appears in my list of recently used coordinate reference systems. But the code is EPSG 26916. And over time, you'll develop an awareness, if you haven't already, about the different types of coordinate reference systems. And it's not really important to describe them all because this is the one we're going to use. The link scales are going to be in meters. And this is exactly what we need to essentially do the interpolation. And we're going to have this box down here that says add saved file to map, and then there's nothing else to set down here. And so we'll just click OK. It is going to give you a warning about converting the data, and just acknowledge it. But if you scroll down here, you can also see that it's going to highlight the region of the coordinate reference system that you selected. And what you want to make sure is that your plus sign, generally where your data are located, fall within that red box. In this case, they do, because we know that this zone 16N corresponds to our little footprint along the Gulf of Mexico. So click OK. And the new dots line up over the old ones, as we might expect, because we really haven't done anything to them yet. I'm going to go ahead and get rid of the original text file, delete that, so we're not using it anymore. Now you would think, well, I told it to export, save as a shapefile, and use a different coordinate reference system, so it must be done, right? Well, if you go up here and open the field calculator and look at the values, you will note that it actually did not change the longitude and latitude from geographic coordinates to UTM coordinates. This is a weird artifact of QGIS for some reason, that it will attach the coordinate reference system to the file, but it will actually not change the data. So you have to do that using this thing up here called the field calculator. So we're going to click on that little abacus looking thing. And there are two ways we can do this. We can create new fields, or we can update existing fields. In this case, I'm going to go create a new field for my X and Y coordinates, which will be in UTM. So I'm going to call them XUTM. And I'm going to select the field type as decimal. And output field length, total length of T10 with 3 decimal places should be fine, because again, we're now working in meters. So we'd be down to the millimeter scale. It's really not necessary. So you could even change this to 2 and it'd be fine. The functions or expressions that you put in here, basically they all exist over here, and you can look at, it's pretty easy to query and find different things, and there's a little help menu over here, but I'm going to just cut to the chase. When you are converting your coordinates, like for the X coordinate, it's going to be $X, and that's going to convert our longitudes and geographic coordinate system to the X coordinate AUTM. And you'll get a little preview of what that value looks like down here, and click OK. And we're going to go back to the abacus and basically do the same thing. We're going to create a new field for YUTM. We're going to select decimal. Don't forget to do that. I'm going to change this to 2 $Y. Look down here. It has changed it now. Click OK. And I'm going to come up here and click Save Layer Edits, and then I'm going to click the pencil to stop editing. And then now, if we go open up our field attribute table, you'll see that in addition to the longitude and latitude, solar level, significant wave height, peak period, we also have an XUTM and YTM coordinates over here, which is what we're going to need to do the interpolation. So now we're going to go and experiment with interpolating these data to create basically a regularly spaced grid of hazard data around Dauphin Island and over it. The easiest way to do this is to open the processing toolbox, which you get to in the menu processing, and then toolbox, got a little gear icon there. I already have this open in a menu over here, so I'm just going to use that. In the search field, if you just type in interpolation, you can type, I can't. You're going to see a number of things pop up. The ones that are popping up here are ones that I've recently used. But in here, QGIS has like these 4 things that pop up as native interpolation features. One is called a heat map, the other is line density. Those aren't things that we're going to use. We want to look at the IDW, which stands for inverse distance weighted interpolation, and the 10 interpolation stands for triangulated irregular network. We're going to demonstrate both of those, so you see the difference between the methods and what they do. As it sounds like the 10, or the triangulated irregular network, it's going to triangulate the data to try and do the interpolation. And in the inverse distance weighted method, it is going to essentially look at the distances between of a bunch of surrounding points of data for every single point that you're trying to get a value for. And it is going to weight the values of those points inverse to their distance. So like points that are further away from the point that you're trying to get a value at are going to be weighted less. Points that are closer to the point we're trying to get data at are going to be weighted higher because they're closer to the point of interest. So we're going to see kind of the ramifications of using both of those in this tutorial. So let's double click on IDW interpolation, and we're going to select our vector layer. In this case, we only have one, so it's pretty easy. Our interpolation attribute here is not the coordinates. It would either be the still water level, so like the surge elevation, if you will, or the wave height. So I'm going to do the still water level for this one. So select what you want to interpolate and click the plus sign to add it. You would want to read up here on, there's a little explanation over here, by the way, of what this is doing. You'll want to read up on some of these things like the distance coefficient for IDW interpolation. It's pretty easy to find information about this. It's not specific to QGIS, but you can find it by including that in your Google search. But inverse distance weighted interpolation is a general interpolation scheme that is not specific to QGIS, so it applies in lots of different things. So you can find a lot of information about what the math behind the interpolation scheme looks like and how this distance coefficient gets applied. We're not going to manipulate it too much because as we're going to show, the IDW interpolation does not really give a good result. So we're going to use 10 interpolation as well. But I would recommend that you play around with the distance coefficient and make it really small and make it really big and see what it does to your results, just so you become familiar with the general trend of how that distance coefficient impacts your overall results. In this case, you do have to select an extent over which the interpolation should occur. In this case, since we don't have any other data sets in QGIS, I'm just going to do calculate from layer, and I'm going to interpolate it over the entire layer of data that we're working with, so the 50-year return period shapefile. In this raster size, now you're going to define how big or how well resolved, how close or far apart your interpolated points are spaced. And remember, we're now working in a projected coordinate system, UTM, in meters. So if we wanted a grid with a point value every 0.1 meters, so every 10 centimeters, that's going to give us over that field of data a grid that has 102,381 rows and 307,472 columns of data. That is way too much. So just to make this go relatively fast, let's do 20 meters by 20 meters. And the reason why I picked that is because a lot of the residential lots on Dauphin Island specifically are about between 60 and 80 feet, but I would say wide, so like parallel to the street, the dimension parallel to the street. So a distance of about 20 meters should give us like at least 1 point per lot in that direction. And then obviously if the other dimension is longer, then we might get multiple points. Down here, you can either just run it as it is right now and it will save it to a temporary file, or you can actually give it a file name here. Because I'm going to trash these, I'm just going to go ahead and click run and let it do its thing. So it'll chug away and then you'll get this data. And it'll pop up here. And so what you're looking at now is basically like a picture of the data values, and the coloring corresponds to this legend over here. So in this case, the lighter the values, the lighter the color, the higher the value. The darker the color, the lower the value. So we've got a bunch of higher values of the surge elevation along the front side of Dauphin Island, which we would expect. And then comparatively speaking, up in the bay and the sound, lower values, which again, we would expect. So really nothing of amazing significance there, other than it looks like this data set has the chicken pox. And this is one of the artifacts of using inverse disinterpolated interpolation on a very sparse data set. So this is not going to work real well. We would need to generate a raster of this resolution. We would need many more data points with a little bit better spacing in the X and the Y coordinates. So this is clearly not going to work for us. But I'm going to leave that one there just for a second. And I'm just going to uncheck it and move it down to the bottom of the list. I said I wasn't going to do this, but let's just do it real quick. Let's go ahead and change that distance coefficient. I'm gonna do something crazy and like multiply it by 5. So we'll make this thing really big so you can see what the effect is. I'll select the extent area again. We'll set the coordinates to, or the resolution to be 20 meters by 20 meters, and then click run. And it'll chug away, and it's going to give us, okay. So essentially what happened was it's starting to kind of smear out the data, if you will, and get away from so much reliance on the value of the point at the point itself, and it's starting to smear those out. So this kind of looks more like a tortoise shell effect now, which is honestly in some ways probably moving in the right direction, but still is kind of crummy for what we want to do. So again, you can play around with those, changing those values all you want. You don't ever really end up getting a satisfactory result for what we're trying to do on Dauphin Island. So let's go ahead and try the other one. So let's try the triangulated irregular network. Again, we're going to come down and select still water level. We're going to add that. We are going to do, you can try either one. They don't give you very different answers. So I'm just going to stick with linear. Then I come over here and select, I want to interpolate this. The extent is the extent of our data. And then come down here and again, select 20 meters for a resolution and click run. It does it very fast. The good news is that even though this looks a little weird, it's actually starting to give us a field of data that's a little bit more representative of what we might expect to see out there. So instead of having these little chicken pox of very high or very low values, we've got more of like a continuous spectrum or a gradient of change moving from one side to the other. If you were just paying attention in the video, unfortunately, it just turned 10 p.m. And we have now just gone into dark mode, which is totally screwed up the display in QGIS. So I'm going to see if I can fix this by just tricking it. It's probably not going to work. So this is not great because you're not going to be able to see anything now. But anyways, at this point, if you were happy with your interpolation and you had the grid the way you wanted it, essentially at this point you have a raster. It's just not saved yet. You could do some other things to clean it up. Like if you wanted to trim this down to a box that looked a little bit cleaner than this random spacing, you could do that. If you wanted to play around with some of the other triangulation features, you could do that. But this is essentially the process by which you develop the raster. But now let's save it because this is a temporary file. So just right click on your interpolated data set and you're going to do export, save as, and then the raster file type is always going to be a GeoTIFF. And so we're going to give this a file name. I'll go back to that file. I'm going to call this DI 50 year SWL 20 meter. So just to remind myself that this was for the 50-year return period event. It's the still water level that's been interpolated, and the interpolation resolution is 20 meters. And then click Save. And then down here, if you wanted to change any of the information at this point, this is where you do it. If you needed to change the extents, if you need to change the resolution, you can up or down sample there. I don't recommend it at this point. You can just save it, click OK. And in that case, I had it the check mark, the box checked to automatically load this into the QGIS window. Now I can get rid of my temporary layer. So now I have my, and if I wanted to, I could drag this down so you could see the data over top of my raster. It's always good practice, I think, to go and just look at some random points in the field to see how well your interpolation did. So if you select your original unstructured data points and use the information tool and just go click on one of these points, you'll see that in that case the still water level was 2.439 meters. If you then click on your raster and click on a point right next to it, you see that the interpolated value is 2.474. That's not too bad. If you get a little bit closer, it probably improves. But that's not a horrible agreement whatsoever. You could argue that the point was 2.4, and this maybe is 2.5. So that's not horrible for what we're trying to do here, which is really just to get a rasterized version of the hazard values. And so you would then do this for the wave heights, for the wave periods. If you needed for winds or wave directions or whatever it was, you would just load in those data and then do that process over again. And of course, you would do this for any field of interest and for all the return periods of interest. And it's a pretty fast process once you get used to it. And then one of the things that's nice about having a raster loaded in QGIS is that you can do all sorts of automatic sampling. So if you had a bunch of like center points of houses or road, which was like a line feature, you can extract the data along those points or line features directly from the raster, and QGIS will just pull those values out so you don't have to point and click around. But just note that this raster is essentially an image file, so you're looking kind of at a picture of your data, and it's gridded. It's whatever resolution you gave it. So that is the process for creating a hazard raster.